Hello, everyone. Welcome to the first normal talk of the day. By RUBYCONF putting me in this slot, they demonstrated two things. One, that they don't understand what I do in the evenings. And two, they give me a chance to give you guys a little advice on the whole rest of the conference. So, those of you that do know me that I am extremely logical. So I will point out two things to you. One is, when you are sitting in the chairs, it is recommended that you sit inward next to the people in the middle so that when people come in, then they can sit on the edges and not have to stand in the back or on the sides or what have you. So I would say throughout the rest of the conference, try to do that, because normally I come into talks late, and then I'm sitting on the side, and then I have to stand the whole time, and then my talk is next, and then I've been standing for an hour and a half. So keep that in mind. The second thing is, and I want you to try this, maybe you've never done it before, but you come to these conferences, you fly across the world, you fly from Europe, from Asia, or maybe just from the United States, from the other side of the United States where things are so different, but you come here to watch presentations. You don't come here to work on your website or to chat with your friends or to be in the IRC back channel making fun of me. So just once, pull out a pad, a paper, and a pen, and as you watch the presentations, write down ideas that you have while you're watching them. And I promise you that you'll have a completely different experience for the whole conference if you do that, because I used to open my laptop when people were talking and start working. And studies show over and over that humans cannot multitask. We really, really suck at it. So if you're working, you're not listening. And if you're not listening, then why are you even here? That's all I'm going to say about that. My name is Preston-Werner. I co-founded GitHub 2 years ago. And since then, it's been amazing how many of you have used it. Oh, you're going to raise your hand? Okay. I was going to save the hand raising for a moment from now, but you can do it now. Unicorn, yes. Let me tell you a little story about the unicorn. The reason that the unicorn came into being is because the unicorn means stuff is really, really wrong. So when you see the unicorn instead of the octocat, it means stuff is bad. He came about when we moved off of Engine Yard onto our sharded architecture, etc. He tells us when the unicorns are not even processing or doing anything. So that's why we have a unicorn now. This talk is called BERT and Ernie, Scaling Your Ruby Site with Erlang. However, before I jump into that, I'm going to do a little bit of a derailment to something else that I feel is very important and needs to be talked about in our community, in all programming communities, and that is that I believe that NIH syndrome, or not invented here syndrome, is a myth. I get this thrown at me every once in a while, specifically because of what we're talking about today, the BERT and Ernie stuff. But when I hear it, it makes me a little sad for the person that just said it. So let me demonstrate by making everyone in the room raise their hands by asking you a question. How many people here on a regular basis use light bulbs? Okay, everyone except the Amish people in the room. How many people here use transistors? How many people here use Ruby? How many people here use Nginx? For the sake of the video, that was basically everyone in the room every single time. So let me ask you then, if we use all of these things, what was so wrong with the counterparts? What's so wrong with candles? Why did Edison not improve the candle by making a better wick? He went a completely different route. Why did the three guys that invented the transistor, the solid-state transistor, why didn't they just make vacuum tubes smaller? Why did Matz invent Ruby? What is so wrong with PHP and Perl? I mean, come on, right? Just add a class system to PHP and you're done. The point being is that sometimes new things do need to be invented. And I think that when people say NIH syndrome, what they're really missing is the opportunity that these new things can bring to bear. So let me tell you a story about when I was a kid. This is not me, but this guy's got awesome hair. When I was a kid, I used to play outside a lot. I grew up in Iowa, and we had a lot of rain and a lot of dirt. And those are basically the things that I played with because there was nothing else in Iowa. No offense. But I would go out as a kid, and I would play in the dirt and the mud. And my friend Tim and I, we would be playing in the front yard, coming up with concoctions and putting grass in them. And I remember very specifically that once I said, after I'd created my grass and mud creation, I have created the cure for cancer. This was the cure for cancer. All you had to do was eat it. But the point of this story is, as little kids, we're always inventing things. We're always creating things in our minds. We're always looking for the next big thing. We want to be special. We want to be important. We want to invent things. So what is it that when we get older, we now start saying, you created something new that looks like something that I'm using, NIH. Why do we do that? I think it comes down to different types of programmers. So I think there's maybe 3 categorizations of programmers. The first ones are the people who just work their day jobs. They're making websites. They're writing bank software. They're just doing it. And then when they go home, they play video games or they do whatever, right? But they go home and they're not programming. It's just a job to them. They don't love programming. They do it for a paycheck. We call those Java programmers. Whoops. The second type is the kind of programmer that uses everything that's available to them to create awesome software, but it's more customer-centric. You're building websites for clients. You're building tools for people to use. But you're not really distributing those. You're crafting them. They're very nice pieces of software, but you're really just using what's available and creating something for yourself or to sell or something of that nature. And I would call those types of programmers craftsmen, the people that rely on what's already there. They like what's there. They're using it. They're not really producing things for other people to use. Those are craftsmen. Craftsmen are great. A lot of us are craftsmen. My friend, who's a computer programmer, just took up woodworking, and he's becoming a craftsman of wood. I think that's really enjoyable. That's a great thing to do. There's nothing wrong with this. However, what I think is more important is the third class of programmer, which would be the inventor, the person that is not satisfied with what is already there, the person that has to go out and create something new every single day. Those would be the inventors. So inventions, I think, are not always incremental. It's not just make a better wick for a candle. It requires jumps of understanding. And so just improving something that already exists sometimes isn't enough. You have to take a logical step outside of what is already there and try something completely new. And maybe it'll fail. And maybe it's actually a stupid idea. But maybe it's genius. Think about this. Think about the future. Every sci-fi movie you've ever seen, put it in your head. Think about all the awesome, cool stuff. Think about Star Trek. They got tricorders. They got spaceships. There's a giant canyon in Iowa. Apparently. But think about that, and think of all the devices and inventions that they have in the future that we don't have right now. There is a mathematical theorem of which I forget the name, but it essentially states that if you have 2 points on a continuous function, then you are guaranteed that that path will go through the midpoint on the y-axis between them. It seems very intuitive. So think about down here as the present. You can't see it. It really says present on the left there instead of isn't. Think about that as the present, and the future is up here. And all along here are all the inventions that have to be made in order for us to get to the future. If that's true, if there are so many of these things, then I would suggest that each one of us should be creating that one right there. Create one in the middle. All of these things need to be created, and they can't all just be improved from what already exists. Sometimes you have to create something new. So you might wonder, how do you go about doing this? How do you go about inventing things? Maybe it's not really something that you're used to. Maybe you're a craftsman and you haven't invented a lot of stuff lately. So what is the process by which you create new things? Well, step 0 It's not really a true step in this process. Read the fucking manual so that you don't invent something that's already been created. Maybe you just misunderstand it. Maybe it already does exist, but you're ignorant of it. So be careful. While you're inventing things, make sure that you're not just replicating something that someone's already done. Make sure there's some new truth, some new thing in there. Step 1, do not accept what already exists. I'm a very picky person. When I use software, if there's something wrong with it, I get angry. Maybe not angry, but disappointed or finicky. It doesn't make me feel good to use it. There's a lot of software out there like this. That the API is weird or it doesn't do thing X or Y that I need. And a lot of people would say, well, why not just use it and maybe add a little on top and then it'll be perfect. A lot of these things aren't that way. So step number 1 is don't just accept it. Don't accept the things that are wrong in your world. Think about them. Write them down on your little pad of paper every time you think of something that's annoying. When you're on an airplane and something's annoying, write it down and then invent something to fix it. Every time something annoys you is an opportunity for you to invent something new that fixes that problem. Step number 2. When you are thinking these things that annoy you, or whatever, recognize that you're probably not the only one that has that feeling. If there's anything that I've learned from the open source that I've done, it's that if I solve a problem for myself, I'm probably solving it for someone else. And that helps me go forward on a project. For instance, I created a project called God that's a process monitoring framework. I created that because I didn't like Monet. I didn't like the syntax of the configuration files. I didn't like the way it was managed. I didn't like a zillion things about it. It never worked for me. I couldn't get it to run on one of the servers that I was running. All of these little things added up, and I said, well, maybe there's a better way to do this. Maybe I can do this completely differently. Maybe I can do this in Ruby with a better syntax that's just Ruby for the configuration file where I can actually use loops and things. What a concept. But these are the kinds of things to think about. And it turns out a lot of people have these similar types of frustrations. And so a lot of people use God to manage their servers. And it turned out that that was a good project. Similarly, something like Chronic, which I wrote, which is a time parsing library. There was nothing there that did what I needed. There was date.parse, but you can only give that a very strict set of things to do. So I said, well, maybe something new needs to be done. And I didn't even look very much at what existed because I wanted to just blank slate it. I wanted to say, I don't care the approaches that anyone else is taking. This is a case where sometimes reading the manual is something not to do. But you have to be careful. You have to choose those carefully and say, I want to do this my way without relying on what other people have done, the approaches that they've done. This was also a learning experience for me to do this. But to give it a new approach, a completely new implementation for date parsing that you could use in Ruby and just pass it natural language. So pay attention to the things that you don't like and realize that a lot of people probably don't like them either. And the third thing is spend some time thinking. I was just on an airplane a lot over the last 14 days in Europe. When you're on a flight, you can do several things. You can watch a movie, you can read a book, you can sleep. But what I like to do is just sit there and think with my eyes closed, and a pen in hand, and the little napkin that they give you in front of me. I just think about things. And when ideas come to me, I write them on that little napkin. And then when I get home, I pull out that napkin and I say, hey, look at all these little things I thought about. Actually, I was thinking about some of the things for this presentation on the way home. I wrote them on a napkin, and now they're in this presentation. So take some time to just think about things. Think about the things that annoy you. Think about the things that could be, the things that need inventing that don't exist yet. And then to choose the ones that are relevant, it should be almost obvious to you which ones are relevant. They should just feel right. Use your intuition. If something that you're thinking about feels awesome to you, then it probably is. Sometimes it's not. Sometimes we're a little eccentric and we're weird. Sometimes that's not true. But often, I find, for me at least, that that's almost always true. So if it feels right, give it a shot and see what happens. Okay. So now that we know how to invent things, we're going to talk about inventing the new GitHub, or specifically the new backend for GitHub that runs the site right now. Maybe you're on GitHub right now because you didn't pay attention to me and you're actually working. If you are using all of the stuff that I'm about to talk about. So as many of you know, we recently moved off of Engine Yard to Rackspace. We did this primarily because we needed more flexibility in the hardware that we could run. We are now running 17 hardware machines that run GitHub. So let me explain the problem that we had. The problem is essentially this. This is what the site looked like on Engine Yard in a much simplified view. We had a load balancer that distributed requests to several front ends. Those front ends would then use the library that I wrote called Grit, that is a Git binding for Ruby. It uses Grit to communicate to the shared file system, so every server, every front end, had access to what looked like local disk, but was actually GFS, Red Hat GFS, running this shared file system. All of the front end machines would connect to that system. The problem with this is when you start connecting a lot of machines to GFS, like we did, and you start just pummeling it with I.O., like we are doing, just insane amounts of I.O., because we're always reading off disk to get information about the Git repositories. If there's any problem at all in GFS, if there's a locking problem, or if one of the machines goes down and the fencing isn't right, the fencing is what takes a server out of the lock pool for GFS. When things go wrong, then you're totally and completely screwed. Because everything in that whole system relies on that shared file system. So when anything goes wrong throughout the whole system, the entire site goes down. And this is bad. We do not like this. So when we moved to Rackspace, we decided that we would eliminate shared file systems. We would get rid of them completely, and we would move to some sort of federated or sharded disk system. So essentially what we want is something that looks like this. Load balancer sends requests to a number of front ends, which now make calls somehow to get the information from the Git repositories to many different file servers. And this, as you'll realize, is the fundamental principle of scaling cheaply, which is take one thing and turn it into many things. This is how we spend a little amount of money and get a lot amount of scale. Because these are just, these file servers, these can just be commodity machines. Each one of these costs something like $600 a month at Rackspace. And it has 1.8 terabytes of storage that's rated for 0.9 terabytes of storage on each one of these. And they still cost very, very little in the grand scheme of things. So how do we do this? How do we say, here's front ends, here's back ends, or file servers, whatever you want to call them, and how do we get the front ends to talk to those file servers in an intelligent way? How does that happen? Because before, it was just all local disk access. It was easy. Use Grit, repositories there, call it a day. But now, something has to happen where the information from Git repositories has to travel over the wire to the front end and send that information back and forth. So there's two problems. There's two problems here. One of them is, how does each machine, how does each front-end machine figure out which back-end machine to talk to? Because your repository could be on any one of these 4 file servers. It's completely arbitrary. So what we did is we introduced a routing proxy that all of the front ends connect to directly. And then from there, it's redirected to a specific machine. We do that using a project called Proxy Machine that I wrote. This is the GitHub fragment that you can go to check this out. This uses Event Machine, so it's super, super fast. Event Machine, if you haven't used it, is probably the most amazing piece of software in the world. It means you can write fast servers in Ruby, because all of the event stuff is written in C++, I guess. But the idea behind Proxy Machine is that you can use a little snippet of Ruby to become a router for this proxy. So front end connects to the proxy. Proxy takes whatever's in there, extracts a piece of that information. This is what we would call layer 7 or content-aware routing. It inspects the request. It figures out what user you're talking about. It does a lookup. We use Redis for a routing table. and the information about where your repository is stored is in Redis, pulls that out, figures out where your repository is, and then just establishes a straight proxy with the final file server. At that point, stuff just goes back and forth like normal, and you're done. Everything is in C++. It never touches Ruby again at that point. So it's extremely, extremely fast and very, very stable. The second problem is what is going over the wire? What are the bits that are crossing this chasm? How do we do that? We decided to use a very simple approach that worked with this architecture, which is a very simple RPC. So that the front ends can just make a call to the back ends and say, give me information about something. By doing this, we maintain kind of a single picture of our application, a very simple, serialized, traceable stack through the whole system to do this. You could use something like AMQP for this. We decided not to. I don't think it's a specifically appropriate choice for this application, particularly because we're often transferring megabytes of data over that wire. We don't want to store that somewhere. We'd rather it not be stored anywhere and just be immediately returned to the caller. And because we're using Ruby, everything is generally serialized anyway. There's not a whole lot of parallelism per process. So this solution fits pretty well. So it came time to choose an RPC mechanism. There's about 1 billion of these out there. Things like thrift and protocol buffers, Corba, JSON RPC, et cetera, et cetera. The list goes on and on. When I was looking at thrift and protocol buffers, those were kind of the first things that I looked at. I'd used thrift a little bit before at PowerSet, where I used to work. The main problem here is IDLs, or interface definition languages. These are the specifications that you write that say, here's the calls I'm going to make, and here's the schemas of those calls, and you express in intimate detail your complete knowledge of this whole RPC mechanism that then forward every developer on your team will have to have intimate knowledge of and modify every time any of these calls ever changes. So as you can see from my vitriol, I'm not a huge fan of IDLs. I don't think that they are appropriate for my needs or for the needs of many small businesses of teams that are small enough to where you're using agile practices, you're using things like unit tests. You're basically doing things the Ruby way. I don't think that's something that's necessary. Maybe for giant companies where things are talking to everything else and every department has to know kind of what things they can use, maybe these IDLs are actually useful, but they're not useful to me. The other thing that I don't like in a lot of RPC mechanisms is code generation. You take these IDL files and you plug them into some program, and on the other side comes just thousands of lines of stub code for your RPC calls. And then you call them just like you would normal code in your application, and then magically things go over the wire and you're done. The problem with this is, one, that every time your IDL changes, you have to regenerate this code. If you're using a static or a compiled language, now you have to compile this code. It's a lot of steps. And sometimes this generated code is pretty bad because you have the authors of these systems writing these generators for languages that they don't even really know. One example would be the Erlang bindings for thrift were some of the most horrible code on the planet. This is now perhaps remedied, but it's a lot of extra work that someone has to do to write these generators, to make this code that machines wrote, that do stuff and hide stuff from you and makes things magical. I don't like any of that. I don't like that whole process. Because what I want to do as a programmer is make a call to something that exists on the back end, and if it's there, it works, and if it doesn't, it throws an exception. Just like every other day in my programming life in Ruby. If I want to call a class, or if I want to call a method on a class, I call it. And if it's there, it works. And if it's not, it throws an error. So I started looking at JSON. I like JSON. JSON is really nice. I especially like the concept of taking a piece of a language, a notation in this case, take that and just rip it right out of the language that it's from and say, hey, everyone, whatever language you're using, now you can use this for inter-process communications. I think that's a cool idea because it's something that already exists. It's already been shown to be useful. A lot of people use it. It makes things in certain languages super, super easy. Target languages like JavaScript, if you're consuming JSON in JavaScript, it's ridiculously simple to use it. So I was thinking about this on an airplane, perhaps. I don't remember. And I was thinking about the work that I did on a project called Electricity, which allowed you to kind of glue together Ruby and Erlang. You could make a Ruby program that would act like an Erlang node and send it messages and respond to it, but you could write all of that in Ruby. So it was really nice for those things that you wanted to write really fast, and you didn't need the high concurrency kinds of things that Erlang gave you. Use Erlang for the high concurrency server type stuff that makes all of that threading nonsense go away, and then you use Ruby for your application kinds of code where you actually need to get stuff done. So I started thinking, there is something in Erlang. Let me take a minute. How many of you have written Erlang before, ever? Okay, quite a few, maybe half, a little less than. That's awesome. I had the pleasure of meeting all three of the guys from the Erlang movie, Joe, Mike, and Robert, and they were all amazing people. I met Joe Armstrong at the Erlang Users Conference in Stockholm about a week ago. He is one of the most animated, intelligent, and awesome people I've probably ever met. This guy is truly very, very intelligent. It was truly a pleasure to meet him. I'm a big believer in Erlang. I've been using it for more than 2 years now, maybe 2.5 years. How many of you were actually at the Ruby conference where they showed the Erlang movie as a joke? Guess who the joke's on? It's on Ruby. Because Erlang can do things that Ruby can't even dream of. You can write servers in Erlang that put Ruby to shame. Now, things like Event Machine mitigate that a little bit. Event Machine is really, really nice. If you want to write servers in Ruby, you better damn well be using Event Machine, because if you're trying to use threads in some sort of server with Ruby, just give up. Just throw that code away and start over with Event Machine. I promise you, you won't regret it. But if you're writing really sophisticated servers that need to do all kinds of crazy stuff and have really heavy concurrency and take just ridiculous numbers of connections, give Erlang a shot. It makes dealing with multiple paths through your system and spawning up functions, doing the kinds of things like forking off a process for each connection, it makes that stuff really, really easy. So I was thinking Erlang. Okay, Erlang has something that it calls the external term format, and that is a serialization that it uses to do certain kinds of communication between nodes and other types of things. This is a very simple serialization that just takes each of its known types. It has little identifiers for them. It looks something like this. So you have a small array on the top. That would be an Erlang syntax, called a term in Erlang. When you serialize this using the external term format, you can use the call in Erlang is called term to binary. And then you put in the term in there, and it spits out a binary. The two angle braces here, that's the binary syntax. So in Erlang, this is a binary. It essentially looks like this. It's very simple. The 131 is like a magic number. The 107 says, hey, you're about to get a small array. 03 says the size of the array, and then 123 is the content. So it's very simple. That's essentially what the protocol or the serialization looks like. It supports all of the types, basically, of Erlang, which are these, things like integers and atoms, and it even has references and ports. You can even serialize functions in Erlang and pass them around. So I was looking at this. I wrote a C version of the decoder in Electricity to make the process of decoding the external term format a lot faster for Electricity since we were using it. I used it with Dave Ferrum on a project called Fused. That was a server, an Erlang server front end for Rails applications. It used Yaws or Moki Web to do that. So I was thinking, I have this RPC situation. I don't like a lot of the RPC things that are out there. JSON RPC has problems where it doesn't have first-class binary serialization. You have to convert everything to base 64, and that's just conversions and dealing with Unicode and all that is just a huge pain in the ass. So I wanted a binary serialization, and yet the binary serializations like thrift and protocol buffers I felt were really lacking because of things that I already mentioned. So I said, what if I took that idea from JSON, where you rip something out of a language and say, hey, everybody use this, and applied it to Erlang? What if I took the external term format and I reduced the types that it supported to just the ones that were common across all languages? So remove things like the functions and the PIDs and the references and all that stuff that things like Ruby and JavaScript have no idea what the hell those things are. Just remove them, but keep the rest of the protocol, the serialization protocol, exactly the same. What if I did that, made a little specification around that, and gave it a clever name and said, hey, everybody, use this? So that's how BERT came into being. BERT is binary Erlang term, much like JSON. It's like a name, right? It's name-like. I guess BERT is a name spelled this way. It's pretty uncommon. You've got JSON, you've got BERT now. So here is an invention that I had, something that I thought might be useful. I think this is something that is really useful in general to a lot of people. A binary serialization that's an extraction from an existing language, already proved to be useful, has really rich types, and can be used for all kinds of serialization and transport things. So let me talk about BERT for a little bit. Here are the simple data types in Erlang syntax. You've got these guys: ints, floats, atoms, tuples, byte lists, lists, and binaries. And on top of that, I said, well, these aren't really complete. I would like to be able to send things, or I would like to be able to serialize things in different languages like hashes, for instance. Here we have nil. There's actually a nil in the external term format that's specified, but it is just the empty array. And so to disambiguate for other languages, we wrap it in these complex types. Each complex type starts with the atom BERT to say, hey, this is about to be a complex type. So that's the only reserved word in all of the BERT serialization. And then we say you can have nils, booleans are just true or false. Dictionaries look like this. You can serialize times. And because I'm a little insane, you can even serialize regular expressions. So again, this is exactly what the external term format looked like. It's no different. It's completely the same. But now this I would name a BERT. If you look at it with a certain pair of glasses in the BERT style, I would call this a BERT because the two are compatible. It's just that BERT is a subset of external term format. So how do we send these BERTs over the wire? Well, we send them with burps, of course. Burps are binary Erlang packets. It is simply just the BERT with a 4-byte header that represents the length in this specific ordering. So 0007 and then 7 bytes of stuff. Very simple, just 4 bytes, always 4 bytes. That allows you to send quite a bit of information over the wire before you hit the cap, and if you're sending that much stuff over the wire, then you probably shouldn't be using this stuff. So now that we have a serialization for data and a way to send them over the wire, how do we use this to solve the RPC needs that we had? We do that with BERT RPC. BERT RPC is a super simple RPC formalization that we now use on GitHub. I'll go over real quick. In the first place here in the tuple, you have either call or cast. In this case, it's call. That says, I want a response from this call. Then you say, here's a module. So in BERT RPC, you can have different modules. So maybe one module that does communications for one system and another one for a different system, just to keep things apart. If it was just a function, you'd have only one namespace. This, having a module, gives you 2 namespaces because the next item is the function name that you're calling. And then the next item is an array of arguments. If there are no arguments, then that would simply just be an empty array. And from this, you're always going to get a response. If it is a successful response, the first item will be reply in the tuple, and the next item will be whatever term it is that was sent back. In this case, the addition of 1 and 2 is 3. The other thing you might get back from this call is an error. big old error message. So we say error. This is a server type error of this error code, and this was the name of the exception, and here was the message of the exception, and here's the stack trace of the exception. So you would get either a reply or an error back. We talked about the burps in RPC. Everything is transferred as a burp. A burp is just, the BERT RPC burp is simply just a normal burp, but you're using the term that represents the RPC call, figuring out how long it is, and prefixing it with the correct header. So if you look at how that looks on the wire, it looks kind of like this. You make this call. It converts to this byte sequence. That goes over the wire, and then you get this byte sequence back, and that represents this in the Erlang syntax. Similar to calls is the cast. The cast just says, this is like a call. It is no different than a call, except I want the server to accept the request and then immediately send back no reply. Just the atom no reply in a tuple. That's all it's going to send back. And then on its side, it's going to queue that up and process that. Whenever it's ready and whatever it would have responded, just throw it away. I don't care. We use this a lot in GitHub to isolate systems that could possibly fail and cause trouble, like reporting exceptions. We have something we call failbot, which is a server that accepts RPC, these BERT RPC requests as casts, and says, report this exception, and then the server just sends the response, the no reply response back, and then all of the HTTP posting and all of the failures that could possibly go along with that are completely isolated in a separate system. You can use the cast for things like that. So module function arguments, send no reply back, done. For advanced things in BERT RPC, we have informational burps, which can do advanced things like, this is kind of what they look like. Things like streaming. You want to stream stuff over the wire, like big files. You can do that with BERT RPC. There's a specification for that. It looks like this. First, you send an info burp that says info. This is going to be a stream. There are no arguments for this specific informational burp. You make your normal call and say, hey, I'm going to send you a file called a.jpg. And then you send n bytes, or you send an n header, which says, I'm going to send you n number of bytes. You follow that by the actual bytes. When those are read, then you do that over again, header, content. And when you're completely done, then you just send a 4-byte 0 header. So just zeros all the way across for 4 bytes. And the response comes back like normal. You can do this in reverse for streaming replies. That would be downloading stuff. Looks exactly the same. Visually, it looks a little bit like this. You say, here's my normal BERT RPC burp. And this would be the info and the normal one. And then you've got your header and your bytes and your header and your bytes and your 0 bytes when you're done. Other features of BERT RPC are things like asynchronous casts with callbacks. So you can say, I want this to be a cast, but I want a response to go to another server somewhere else. And by sending an informational burp with the callback information, then your server can then make a BERT RPC request back to that callback address with the response that you would have normally gotten, but you do it asynchronously. It's out of band. There's also some advanced caching stuff. I don't have a lot of time left, so I will allow you to look at that. But there's expiration-based caching and also validation caching, which is like the expiration, the normal TTL stuff in HTTP, as well as the E-tag stuff that allows you to handle complicated validation really elegantly. So the philosophy of these systems is simplicity. To write a BERT RPC client or server is really quite trivial because the specification is so small. There's no code generation. There's no IDLs. I mean, you could write them, but the philosophy is not to. The philosophy is to say, use BERT RPC just like you write normal code. So simplicity plus functionality. What is the most amount of functionality with the most amount of simplicity that we can create? And I would call that BERT RPC. So let's look quickly at some implementations of these. This is exactly what we use on GitHub. The one I wrote is called Ernie. Ernie is a BERT RPC server. This is a complete specification. This is a complete code file for an Ernie server. This gives you full RPC functionality on the server side. You say, require Ernie. Here's a module named calc and a function named add. It takes 2 parameters. Those are A and B. Add those together, and whatever that happens to be, return it. That's all it is. 6 lines of code. You run this with this command here. You say Ernie, demonize it, run it on port 9999. spawn 10 Ruby processes that are running that handler, and then balance between them. Or you could run 20 or 30 or 100 of these, whatever is suitable for your specific task. -H says use this handler, the calc.rb file that you just saw. There is a, and I'll show you that in a second, how that actually runs. There is a BERT implementation called BERT. It looks like this. You just say BERT.encode, some Ruby value, and that returns the binary, and in an Erlang syntax is the second one there. That would be 7. Encode an array, it looks like that. Encode a tuple. There's a little syntax for tuples where you just prefix an array with a T, and that tells the BERT serializer to turn that into a tuple instead of an array. And that looks like that. And then encoding things like times, that takes a little more space, but it looks like that. BERT RPC implementation. So you fire up that Ernie server. You want to call it and get data back. Well, that looks like this. BERT RPC service new. Here's the host. It could be localhost or whatever the name of the host is. The port it's running on, and to call this. And this is where you see the simplicity of the system and no code generation and no IDLs. You just say svc.call. That could be a .cast if you wanted to cast it. svc.call or .cast. Calc, that's the module name. Add, that's the function name, and the 2 parameters. And guess what? You get your response back. That goes over the wire with BERT RPC using Ernie and BERT. You've got like 12 lines of code for a full BERT RPC server-client relationship. Extremely robust using all of this code. I'm going to demo this real quick, running out of time. However, I really want to show you this because it's awesome.
No Erlang involved?
There is Erlang. So here's how it works. So the thing with Ernie is a hybrid system. Ernie is part, what the? So here's Ernie. This is how we started up. So Ernie is a hybrid system. Ernie is a Ruby gem. You just do gem install Ernie, and you've got it. You've got your Ernie binary. But that Ernie is actually Erlang. So what it does is I created a way to package up Erlang applications into a Ruby gem, and then it just uses the normal compilation stuff. But instead of compiling some C extension, it's compiling Erlang. So now you've got an Erlang server that's doing all the balancing and whatnot, and then Ruby handlers that will balance between for all your calls. You start it like this. This says, what does this say? This says, run 8 of these, and you start it up, and you get the standard Erlang spew of starting stuff up. Believe it or not, that was actually successful. And then you call it like this. So I got this loaded already. So we say svc call. There's a, let me show you the, oh God. Whee. So this is the handler. Looks like this. Wow, this is tricky. You got the function add. It looks like exactly like that. And you've got this log file. You can also specify, a log file in Ernie, so it'll spew that out. Let me drag this over. Whee. So this is the, let me clear that. So if we run this command and we say, give me call.test.bytes, and all that does is just generate that many bytes and then send it back over the wire. So we call that, okay, you got X comes back, right, really fast. Wow, RPC, it's amazing. If we look at the log, it looks like this. So we can see that that actually ran. I returned, this is what it received, this is what it sent back. Everything is awesome. So real quickly, I wanted to show you some benchmark numbers. I'm going to comment this log file line out because it's kind of slow. And then I got to restart this guy. So that loads that guy back up. And then if we find here it is. So this is called eBench. This is a little benchmarker I wrote for BERT RPC. This is going to say, this says make 5,000 calls using four threads, 4 processes in Erlang. This is a little Erlang benchmarker. So it's going to run that, and then it's going to give us some stats about how fast it ran, So here we go. It did 5,000 requests at 2476 requests per second through that process. Ta-da! I'm really out of time, so I'm going to blast through these super, super fast. This is how many requests that GitHub has done through this whole process so far since the launch. 626 million. Actually, it's probably like 640 million now. I did this number yesterday. There's a bunch of implementations in a bunch of languages. If you want to help, if you like this stuff and you want to help, write an implementation of BERT serializer or BERT RPC client or server in your favorite language. That is the best way that you could possibly help this. There's a mailing list where we can talk about BERT 2.0 and the things that are going to change. There's going to be some new stuff that I'm going to add and maybe deprecate some stuff. This is the URL that you go to, bert-rpc.org, to find out all that information. The architecture stuff that I talked about was very, very, very basic. If you want a more specific covering of that, just go to Google, search for GitHub Fast, and you'll find the article that I wrote about how we made GitHub Fast. And now that you've seen all this and you're stoked, go invent something new. Thank you.